Hi, and welcome to HEX Biome Generator, Totally Not Catan workshop. My name is Bailey Hogan, and I'll be guiding you as we create a procedural board game environment with shuffled biomes per hex tile. In this workshop, you'll learn how to build a biome generation pipeline using SideFX Labs' new biome toolset. Workshop participants will start by designing a biome ID map in Copernicus with a random tile pattern. This biome ID map will then procedurally drive terrain terraforming, plant scattering, and terrain texturing to produce a fun, shuffled biome board game environment. We'll begin by introducing what is needed to follow along with this workshop. Then we'll get a glimpse at the final result before we conclude this presentation by introducing the lab's biome tools. In the interactive portion of the workshop, we'll explore the biome plant scatter and instance recipe, and then we'll start building the HEX biome generator. Be sure you have Houdini 20.5.522 or newer installed on your machine. Second, install the latest daily build of Labs. From the launcher, navigate to Labs, Packages, and Install. And finally, download the project files from github.com/SideFX Labs examples, where you can clone the repository or download a zip file. In the end, we'll have something that looks similar to this. And in the beginning, we'll also have something that looks like this. And that's because I provided the complete file for you to follow along with. We'll be recreating certain sections of the file, but if you ever get stuck, you'll have the right answers to refer to in your file. This pipeline is completely procedural, so you can adjust the seed and achieve a totally different shuffled board game environment. This is the beauty of Houdini and what we all get excited about at Everything Procedural Conference. And we'll be scattering our low poly vegetation with the latest SideFX Labs biome tools. The Labs biome tools are a suite of tools that scatter vegetation and other natural elements based on real-world properties of biomes, environmental influences, and vegetation interactions across large-scale environments. The toolset is designed to be modular, highly customizable, and production-ready with strong default behavior out of the box, but with enough flexibility to suit any studio's needs. The tools focus on procedural placement, but also offer enough artistic control to feel intuitive and controllable. Here's an overview of the Labs Biome Tools Network. Just begin typing Biome in the tab menu to reveal the full list of tools. I want to give a special thanks to the SideFX Labs team for their support in developing the Labs Biome Toolset and this project. Mai is the lead of SideFX Labs, Danica helped develop many of the biome tools, Christos provided our low-poly plant assets, Mo is our game engine guru, and he has produced tools to export the plant asset point clouds for PCG and Unreal, and our wonderful interns Han and Eddie helped me build this Totally Not Catan project. Han helped design the terrain terraformation and plant scatter, while Eddie generated the terrain textures in Copernicus. I also want to give a special thanks to Arvid Schneider, who has produced beautiful cinematic environments using the Labs biome tools. His feedback on the tools has been so valuable, and if you're looking for more tutorials on the toolset, visit his YouTube channel. This is his latest Totally Not Star Wars environment, generated using the biome scattering tools. Now we'll begin the interactive portion of our workshop by introducing the biome plant scatter and instance recipe. The biome recipe, whose name was recently shortened from biome plant scatter and instance recipe, can be dropped down like any other HDA from the tab menu. This tool recipe is a network of all of the biome nodes needed to scatter plants based on real-world properties of biomes. The example environment is a mountain terrain with 3 different plant species. The aspen trees prefer the warmer valleys, while the pine trees prefer the cooler mid to high range elevation areas, and the hardy shrubs are scattered throughout. There's also lake geometry that is masked from the plant scatter. At a high level, we are adding environment attributes to our terrain here, setting a plant's preferences for those same attributes here, and then matching plants with their preferred environment in the biome plant scatter. Here. I recommend starting with this recipe to learn more about how the biome tools work together, or to just get the biome pipeline set up quicker. Then you can begin experimenting by inputting your own terrain and plant models for a custom procedural scatter. Now let's begin the tour of the foundational nodes of the biome setup. The Biome Plant Define is where we define our plant species preference for temperature, precipitation, and spacing. If you press Enter in the viewport, you'll enter an interactive mode where you can easily set the preferred climate and climate bounds for the plant species by simply adjusting the crosshair and bounds handles on the graph. This is a Whittaker biome diagram that separates different biome areas by their climate, making it easier to match plants with their preferred biomes. There's also a scale handle for adjusting the plant spacing. The red handle scales the plant's bounds radius, and the blue handle scales the plant's trunk radius. Trees have to respect other trees' bounds radius spacing, while shrubs only have to respect tree trunk radii and other shrub bounds radii. This allows shrubs to appear under tree crowns without intersecting their trunks. The Species Variance tab is where our tree models are chosen. This example is pulling from the low-poly model example plants saved in the extra files of the HDA, but you can point the variant to a file on disk or another node in your network if you switch to operator path. You can also choose a dead mesh variant if the dead ratio is set to a value greater than 0. The normalized age range determines at what age this variant of the plant will appear. We have chosen for the smallest tree to appear for plants in the first third of their life, ages 0 to 0.33. Similarly, the median plant is showing up between 0.33 and 0.66, while the largest plant is showing up between 0.66 and 1. You can also adjust the scale range to add more variation to the scale of your plant variant. Moving over to the terrain side of the pipe, Biome Attributes to Terrain is responsible for assigning the initial environment settings to terrain Heightfield layers: temperature, precipitation, soil, and biome color. In this recipe, we are using the default attributes shown here. The same attributes flood the whole terrain because there are no biome definitions and biome regions input into the second and third inputs. If we add these inputs using a biome region assign node, we can have multiple biomes on one terrain. This will be a big focus of our tiled biome board game environment. Next, strong default attributes on the biome attribute evolve node take over to add more realistic detail to our scatter. The environment attributes react to the shape of our terrain to simulate the effects of natural phenomenon like temperature drop with elevation, rain shadow, wind exposure, and soil quality patterns. Finally, plants are matched with their preferred environment conditions on the terrain, and a point cloud of plants is generated by biome plant scatter. In the Visualize tab, we can enable the display of plant points and their spacing radii and control the attribute to color by. If they are colored by plant species, the color will match the species color defined on the Biome Plant Define nodes. Notice red is the color of the shrub, green is the pine, and blue is the aspen. If Visualize Terrain is enabled, you can also see the viability masks of each species. Finally, we add an instance node to the output plant points to instantiate the plant geometry with the correct scale. The biome recipe is a simple example of 3 plant species on a single biome terrain, but next we'll dive into the HEX biome generator project to showcase the biome tools can also manage multiple biome regions with many plants.
Now we'll get into recreating our environment. How I'm going to handle this is I'm going to go over these different sections that have network boxes around them. And the reason I'm not stepping through every single node is you might see some repetition here, and we want to save time. So I'll just go over one, and you can imagine rinse and repeat for every biome. Yeah, so we'll get started. The first thing we're going to do is create some hex tiles, like so. And we're going to create this in SOPs land, add some ID attributes to each tile, and then import the SOPs with the SOP import into COPS land, and that is where we'll add our beach area around these different tiles. So to get started, we're going to use a new labs tool called the Labs Hexagon Grid, and it is really convenient for us because right out of the box, it's already by default creating what we want, which is a hexagon grid. And I'm going to change this to add primitives to go ahead and fill those in. So we're going to keep it on the XY plane and have it facing to where when you look down the negative Z axis, it looks correct. So the normals are facing this way. This is the axis where the Copernicus network is expecting SOPs to be. So we start with the hexagon grid. Next step is to kind of shrink these so we get some borders between them. We'll start with for each primitive, drop that on there. And for each primitive, we're going to do a poly expand. And instead of expanding, we're actually going to shrink. So we'll put the display flag here. And we won't keep the outside. We'll only do the inside. Does that work? Yeah. Okay. So if you mess with this offset, we can get just a slight gap between our tiles there. So for each tile, we're going to shrink it. And then we're going to add a sort node. And this is what's going to be responsible for shuffling our tiles. We'll do a primitive sort random thing. Let's show our primitive numbers here in the viewport, and then you can kind of see super tiny. But anyways, you'll see as I'm moving the seed, our primitive numbers are shuffling, and that'll be important for whenever we're randomizing our board. We're gonna take that primnum and assign it, create a new attribute called ID. So we'll change it from attribute 1 to ID. This is going to be a primitive attribute that is an integer. And for the value, I'm just going to type in the variable @primnum. Let's see if we did that correctly. Okay, so our primnum is equal to our ID. Next, we're going to remap our ID so that we have different clusters of biomes. We're not going to have a different biome for each tile. We're going to have 4 of biome 1, 4 of biome 2, 3 of biome 3, etc. I've kind of modeled it after the game Catan that separates the different resources into 4, 4, 3, 3, 3, 1, I believe. 1 for the desert. So anyways, we're going to remap that ID primitive variable that we just created. And our input is from 0 to, what was our max? 19, 18, 18. So from 0 to 18, which I think I could probably just say compute range. No? Okay. Compute range. Oh, I need to put my name here. Original name, primitive ID. Yeah, there we go. Okay, so this is what it was before. If I hit compute range, now it's working. It's reading that ID attribute. And we're going to remap it from 0, or let's actually do it, remap it from 1 to 6. And we're going to use this map here to define our different areas. And I'm going to be a bit more precise than this, but I just want to give you an idea quickly of how this is going to work. So we'll do constant on all of these. So for the first one, it's going to be at position 0, 0. The second one, it's going to be at a position of, so the first 4 of the 19 biomes, so that position, are going to get the value of 0.2. The second one will be 8 out of 19, and I'll give that one a value of 0.4, constant, constant. This one's 0.2. And this one is also constant, 0, 0. Okay, I think I'm figuring it out. Okay, so then 4 of 19, 8 out of 19. What's our next value? 12. So another 4 steps later. 12 of 19. We're going to give a value of 0.6. The next one will be 0.8. And I think this one is going to be 15 out of 19. So this will be our first 3 group. Let me double check that over here. Yeah, 15 and 19. And 1. This one is going to be 18 out of 19. So only that last one, primitive 18, is going to be given the value of 6. So that'll be our desert on the end. So if we look back at our geometry spreadsheet, those first 4 are getting the value of 1, second 4 are getting 2, then third 4 are getting 3, followed by a group of 3 that are given 4, and then 5, and then 1, 6, and that's our desert. And that's just if you want to keep it like Catan. I'll go ahead and color based on that ID. I'll give it a random color. Random from attribute, and the attribute will be ID. No. There we go. We'll delete all existing color attributes. There we go. This is a bit too big. If we lay down a grid, an XY grid that is size 2 by 2, this is going to give us an idea of the bounds of the Copernicus view. You can see it stretches between -1 and 1 in both axes. So this is going to be too big. So I'll put the display, template over here on the grid. And the way I can scale this down is just by shrinking this radius here. I could also use a transform, but this is fun. There we go. Gonna adjust that. I'm also gonna adjust this offset. Middle mouse clicking, and so I can be more precise with my measurement here. Let's see. Okay, we'll call that good. Let's see. How do I compare? Pretty similar. Okay, so I'll drop down a null and call this out hex tiles. This is out hex tiles 1. The same as this one here. And then we're going to create a copnet, and I'll just redo this on the side here. What we're trying to do is get a different gray value for each ID and also create this white beach area. So we'll start with a SOP import and read that out hex tiles that we just created. Let's see. Period. Out hex tiles. We'll do out hex tiles 1, our new one, to see a difference. Okay, so then we'll rasterize, do rasterize setup. And this, if you look at the documentation for this, that's where you can see that the rasterized setup by default, if you don't give it a camera, looks down the negative Z axis. So if we switch over to our composite view, so after adding the rasterized setup, I add a rasterized geo node, and this is when I can start seeing something in the composite view. And it's just a black and white area. It's bringing in the alpha, but what we want to do is also bring in our ID, and this reads attributes on the geometry itself. So here I'm going to type in the attribute name ID. Let's go ahead and do ID to mono to see if that worked. Yeah, that's working. If you right click, inspect, and here I'm on ID to mono. If I switch this to mono, you can see that value changing. Here's 5, 2, 6. These are the numbers that we are expecting to see. We're going to remap these values so that they're all above 1, which is why they're showing up white. But let's instead remap them. So instead of from 0 to 6, we're going to have 0 to 1. Actually, so the reason I didn't do it to all the way to 1 is because I'm going to save that 1 value for our beach on the outside. So I'll put this at like 0.8. So there's our greatest value of 0.8. And we'll reserve that white value for our beach. And the way we'll achieve that is we'll take this rasterized geo, plug it into our dilate erode, and that looks okay. We don't want a soft edge though. I'm going to keep it a hard edge so we can clearly define the boundaries of our different biomes. I'll go ahead and blend the foreground and the background here. So here's our foreground. Here's our mask for our foreground, and then here's our background. And voila, we have a beach. This is going to be our sandy area, and then black will be our ocean. And to finish, I'll add a null. That is our out biome ID. And this is what we'll read into our biome region assign node. Here's out biome ID 1. And then come back to our scene view. And now that we have an image created that includes both our biomes and our beach, we can create different biome regions with our biome region assigned. Before I get into this, I'm going to show you how we define our biomes. It's very similar to how we defined our plants. So I have a sand, and it's just a crosshair. Sand doesn't have any soil really, like we're not using it as a biome that we're scattering plants on. So I could really just uncheck this soil tag here. But let's look at desert. So here's another crosshair. Again, you can see it's interactive, so you can move around in the viewport. The name is coming from the node name. And I would recommend doing it this way. We've had some errors whenever we try to assign these names to volumes, and they have spaces within them. So you keeping it to whatever the node name is with this $OS prevents those errors from happening. So we'll have underscores instead of spaces. Anyway, side note. Here's the temperature and precipitation for a desert. Same thing. Red rock, mountain. I guess if some of these I'm a little confused by, because I wouldn't really associate red rock with tundra, but really if you want to be scientifically accurate, you can. But the main thing is you want your biomes to be really separated from each other so that your plants can have distinct areas where they are showing up. If you start putting your biomes really close together, then your plants are going to kind of mush and blend and show up in areas where you might not expect them to. So, yeah, those aren't super realistic values, but they'll get the job done. We're not going to step through that process. I will show that if you drop down a biome define, there are presets. So here's one for boreal forest, subtropical desert, and you'll notice that they just kind of center over their different areas on the Whittaker biome diagram. The same thing for plant defines. So if you want to, you can choose these presets as well, which will pull from the embedded assets found in the extra files of the HDA. And I tried to name the recipes after the biome that you would expect to see them in. So they start with boreal and then the plant name. So boreal pine. So that'll help match biomes and plants in the future. So I wanted to show those presets. But what we're actually going to do to speed things along is read from a biome definitions file. So if you follow along, you can drop down this node and read. Let's look at what we have saved here. The biome definitions, HEX biome definitions JSON. And I'll reload. So you're not going to see anything. It's just a point with data on it. So if you look in your geometry spreadsheet, here you can see all of our biomes that have been stored into the geometry. If you do want to see something and be able to edit these different biomes, instead of create geometry, you can change that to create biome define nodes and reload from disk. And what that does is it goes ahead and creates all of your different biome defines. And then you can go in and change your settings a bit more. And this works like a file node. So you can, after you tweak your settings, you add another definitions file and change this to write. And it'll write that file to disk after you press save to disk. So now that we have our biome definitions, we don't need all that, but we'll do our geometry. Here we are. Plug that, or yeah, we'll need a null for this because we're going to refer to it multiple times throughout our file. So I'll name it biome definitions. And then we're creating a height field. For this example, it's 1,000 by 1,000, but it's scaled to 3.75. And we'll also create a null for that because we're going to refer to it elsewhere. And we'll create that. This is all that our biome regions assign requires. The biome definitions as input and the height field. And then within the file, we can change this to read an image, but instead of a file, we're going to read the COP network that we generated. So let's see. What is it? COPNet init biome ID. COPNet init biome ID. And we're going to read that out biome ID one that we made. And to make this go faster, I already know the trick, which is to turn this iterations way down to 1. And then, yeah, finally we'll hit recreate region list. And this will parse out the different colors of our image and assign different biomes to them. It's important to put your put the correct number of color clusters though. So this is the number of sections that it's going to try and divide it. So we want to make sure that our biome region assign clusters are set to 8. And then recreate our region list. So we have sand, desert, red rock, ore, savanna, deciduous forest, ice, and water. And you'll notice I ordered the biome definitions here in the same order as the value on our biome ID, because this is how biome region assign works. It starts with your lightest value, the hue, or it starts with the lightest value and goes down. I think it actually sorts by hue, saturation, and value. But anyways, I know that the lightest values are going to come first, so that's why I listed our sand first. And by default, that's how they get paired up. But if you mess up the order, you can always reassign it to something else. Show sand, desert, red rock, ore, savanna, deciduous forest, ice, and water. Water is that black background value. And it's just a height field, but it has different layers, one for each biome. A way to visualize this to see if you've done it right. Let's go ahead and fix these as well. 6, 7, 8. Okay. Oh, that's 7. There we go. Is you can change that final height field layers to guide geometry. And the sort order determines the height of these different layers. And you can see it's been separated correctly. So there's our different regions. We need to remember to change this back to final height field layers, because that is what our other nodes down the biome pipeline are going to be looking for. They're going to be looking for height field layers. What we can do now is separate the different layers out. So I'll do a height field. Let's see if I need this. Yeah, I'll go ahead and add another null. Anytime you see me add a null, it's most often because not just to keep things organized, but also because I usually am referring to that node somewhere else in the pipe. So out biome regions, height field, copy layer. We're going to copy one of these biome layers to the mask. So from sand, let's fill the mask with that sand layer. Ta-da! And that's how we can separate out each one. I'm not going to do that. You can see how that's done. Here's desert, mask. So we can look through the different ones. Bedrock, savanna, deciduous forest, ice, and water. So now that we've assigned our different regions, we're going to use those regions throughout the rest of the pipeline to first terraform our terrain. So we have our OG Heightfield and our desert. This is just referencing our null here, out desert. And this is just a mask. So that's all this layer is. So we're reading in a mask, and we're terraforming the terrain, but only on that mask area. Here's desert. Here's adding the red rock area. So getting more of this terraced terrain. Mountains. Savanna. So it's these flat ones. Deciduous forest and the ice areas. That's these guys here. And that's how we use the masks to control our terraforming. We can also, before we begin texturing our terrain, we can create new masks using Heightfield mask by features. I'll go ahead and show this process off. Heightfield mask by feature. Drop it in, and let's create one for occlusion. We don't want a mask by slope. Okay, so we'll drop down a mask by feature, use mask by occlusion, remove the mask by slope, and get something like this. And we'll blast to where we're isolating just the mask. There's mask, delete non-selected. And that is what we're going to read into our CopNet to help texture. And you get the idea. These are what we're going to read back into our CopNet. We'll go ahead and dive in here. Do our simplified terrain texture. And you can see why I had to simplify it, because it's already, the simplified version is already pretty big. So the first thing we do is drop down a SOP import that looks at that, the terraformed terrain. Paper/out. Terraform terrain. Here we go. So that brings in our terrain that has all our different biome terraform sections. And we're going to do a geometry to layer to create this masked view. And we'll remap it. We're going to use attribute promote to promote our height to its max height value. And we're going to use that in our remap. So I've converted our terraformed terrain to geometry. Added a UV texture. Along the y-axis, I flipped the scale and changed the angle to -90. And then I'm adding attribute promote to promote height to max height. So from the point attribute height to the detail attribute max height. So if you look at our geometry spreadsheet and our detail view, now we have this float value here for max height. And I created a null that is the terrain max height. And inside the CopNet on our remap, we're going to remap to values from 0 to 1, starting from 0 to that max height. So detail, we'll do a -1 spare input. So detail -1 max height. Use add spare input, and whatever you put here is what that is the -1 input. So we're gonna look at, what was the name of it? Terrain max height. Period, terrain max height. Zero. Okay, I think it expects 3 values there. And yeah, that seemed to work. So we had our height values that were going from 0 to 309. And now they're normalized to go from 0 to 1. So if you check out our composite view, that's something that we can work with in our texture creation. Okay, so we have a SOP import where we're looking at the different named layers that we made here. So here's our sand. Inside our CopNet, we're gonna pull that sand in, and right here, SOP import, out sand, geometry to layer. The reason that we removed our height is because it'll just pull in whatever layer we have. So if we just have mask, it's going to pull in that mask layer, easy peasy. So we bring in our SOP import, geometry to layer, and then we can start mixing and matching these different textures using our biome regions. Let's just look at this desert one. So we have the desert mask, and our foreground is our height. So we'll use this mono to RGB with the ramp to control how this grayscale gets converted into color. And we do the same thing for our red rock. And we keep combining these different masks and adding blends and blends and blends until we get a texture that looks kind of like this. And this is our simplified version. We're referring to it in this material. If we go to our stage, let's recreate our scene. So we'll start with a scene import. And this is just going to bring in our terrain. So our objects, we're going to choose the terrain. Okay, so with the scene import, you want to make sure that whenever you're pulling from the object level, that whatever you're trying to render has a display flag on. So we'll go ahead and go back to SOPs, or sorry, to LOPs. After you've imported your terrain, we can use a biome plant scatter import. And this is another biomes node to make it easy to read in our plant scatter. Before I do that, I just want to be able to show how we're creating our material library for our terrain. Well, let's see, how did I do this? How's the terrain created? Okay, so we do a material text chord and feed that into these material X images. So there's the base color, roughness, normal, and height. And we're reading from a COP network, as you can see. You just have to add this OP in front, and you can read those different images in and plug them in to the correct spot. So base color, roughness and roughness, emissive and emissive. I found that if you don't include this text chord, it doesn't render very well in the OpenGL space. So if you want to see your stuff in SOPs, then I recommend just dropping down one of these material X texture coordinates and feeding that into each of these images. And yeah, that's kind of how it's made for the terrain. I'll just keep showing this side. Here's our Karma physical sky, camera, and Karma render settings, and a render route. But yeah, the big things I wanted to show are bringing in your terrain, adding a material that is reading from the COP network. Next, I'll show the plant scatter. So turn these display flags back off. I'm gonna, instead of doing every single one of these, we're gonna read from a JSON file. Again, you can use presets to help you define these, but we're gonna read from a definitions file. So biome plant definitions file. We'll read that in. And if we need to read it. See if that worked or if I accidentally overrode it. No, that worked. Okay. So in our geometry spreadsheet, again, we can check that the data was brought in. And if you look here, you can see all of the data that was read from that JSON for this particular plant species. Here I'm just looking at geometry, but you can also do plant define nodes and reload from disk. And there you go. You have all of the different plants that were read from the JSON file. We'll leave that as geometry. Also, so now that we have our plants defined, we also are going to go ahead and continue with the biome pipeline. So we have the biome attributes to terrain. And if you'll remember, this is where we define our different regions and give them the correct temperature and precipitation. So let's see what it's expecting. We need our terrain. So we'll bring in our terraformed terrain with an object merge. And we want to be sure to pull in the terraform terrain. That way, whenever we scatter our points, it's on the different height terrain and not the flat one. Because this is what determines where those plants get scattered. So here's our terrain. The second input is the points with biome definitions, which is not the plant definitions, but the biome definitions, which we already defined in our other geometry. So we'll read that with an object merge as well. Out biome regions. So here they are. And then our third input is expecting the biome region assign node. And that is also found in the other network. So we'll pull that in. This is why we made all those nulls. Okay, so I think I might have messed up. So this is looking for biome definitions, not the regions. This one's regions goes into the third input. The second input is looking for definitions. Inside terrain, we have our hex tiles, we have our biome regions. Here's biome definitions, it's right here. Biome definitions. I think what we can also do, if we had like 2 setups here. So we go into our labs view and we go into terrain. This is kind of a different way to do it, but yeah, we'll just drag this into here. Ta-da! All right, so this is actually our biome definitions. If you look into the geometry spreadsheet, here we go. We have our biome definitions. Yeah. And then biome attributes to terrain. We can see if that's working is we can change this input. Here's our different temperatures, precipitation, soil, and our biome color. So here, these colors are actually corresponding to the colors that we set up in our Biome Define. So, well, if we zoom back over here, there's savanna is yellow, water is blue, and that's what those biome colors are reading from. So there we go. Next, we want to drop down a biome attributes evolve. Okay, the first input, if I hover over, is expecting the terrain. So I'll put that there. There we go. There. And then the second input is looking for a mask. So if we don't want to evolve the entire terrain, we could add something there. We can see how that's working. We have different areas that are evolving the temperature and the precipitation. You can kind of see how, as this is getting higher, it's getting cooler. And then finally, I'll add a biome plant scatter. The first input is looking for the plant types, so that is found here with our plant definitions file. The second is our terrain. And then thirdly, I believe, is a mask. So if you don't want plants to show up in a certain area, you can use a mask here. What we've done is we did a volume combine to, let's see, we're reading from our biome regions. Let's add together our sand and our ocean, because those are two places where we don't want plants to appear. Sand, and let's add a water. do maximum, maybe. Destination mask. Can I do that? View mask. There we go. So here's this. And we'll do a mask expand so that it also doesn't show up on the edges of these different biomes because they kind of slope downwards. We don't want the plants to show up there either. So we'll do mask expand. Yep, Heightfield mask expand. So shrinks it in a little bit. And we'll plug that into the third input that expects a mask. So I'll show the before and after of that. Here you can see the different plants represented by their bounding radius, which is the outer circle, and the inner radius, which is the trunk radius. And you'll see the different colors correspond to the different colors that you set on your plant defines. And if I go ahead and add an instance node, it'll spawn the correct plants. So there we go. We'll go ahead and merge that with the terrain. And there you have it. A plant scatter per biome. I think that maybe, if I'm not mistaken, the plant scatter might have had a scale multiplier on it. Let's look. Yes, a scale multiplier of 2. So went ahead and just multiplied the scale of every tree by 2. Make it a little chunkier, more board game like. Here's our plant scatter. If I'll just put the output on the plant instances, and that is what will get read in to the Solaris node. So go over here. Biome plant scatter import is looking at that plant scatter node, and then I'll click autofill materials, which basically promotes the point material that was on the plants to a primitive material. And inside of our material library, we also have a material for plants that is reading in different attributes that were output from that plant scatter. So the display color on the meshes is combined with those different attributes to create some randomization per instance. So for example, we can look at the age that is output from the plant scatter, the noise, or the unique ID. So I'll show you where those attributes are being output. You go to the OBJ, plant scatter. If you look at the optional outputs here, we have one for age, noise, and unique ID. So this is unique per instance, as you can imagine. Age is pretty self-explanatory. Noise, however, I wanted to show you, you can control that here. This just gives like a cloud shadow-like effect to different clusters of plants. So by reading in those prim vars, we can create a varied plant material. And you won't see it here, but in your final karma render, that you'll see it because that's where we created our material, was in with the karma material. And there you have it, a HEX biome generator.